Hello students, we are going to study molecular orbital theory, or also you can say MOT, M-O-T in short. Okay. This was given by F. Hund and R.S. Millikan. Okay. Now, we have studied about the atomic orbitals earlier, isn't it? Atomic orbitals means what? The one atom. Okay. It says about atomic orbital, but when we are talking about molecule, it says about molecular orbital. Okay. So now, how is this molecular orbital formed? You know, this atom combines with another atom to form a molecule. Like that, atomic orbital also combines with another orbital to form a molecular orbital. Okay. Now, there must be conditions then. Can all the orbitals of the atoms can combine easily? No, this can't happen. Okay. It should have a comparable energy. It means there must be not a wide difference between the energy of the orbital. It should be minute, or it should be that only, similar only, or it should be minute. Okay. If energy difference is too much, molecular orbital will not be formed. And they should have what? Proper symmetry. Okay. In this, if the symmetry is different, they will not form molecular orbital. The atomic orbitals will not combine to form a what? The molecular orbital. Now, when we are talking about atomic orbital, एक atom, how many nucleus it will consist of? Only one, na? So, we are saying what? That it is monocentric. Okay, so atomic orbitals are monocentric in nature, having only one nucleus. But what about the molecular orbital? Here atomic orbitals are combining. Naturally, will it have only one nucleus? No, it will have many. It can have two, it can have three. Okay, so these are known as what? Polycentric. If two atomic orbitals combine, it will form a molecular orbital. Okay, so when it is forming a molecular orbital, okay, it will form two types of molecular orbital. That is a bonding molecular orbital and anti-bonding molecular orbital. Okay, when we are talking about bonding molecular orbital, its energy is always low. Okay, but when we talk about anti-bonding molecular orbital, its energy is high. And when energy is low, we say what? It is stable, isn't it? And when energy is high, we say what? It is not stable. Okay. So here, when we talk about this bonding molecular orbital, its stability is high. And when we are talking about anti-bonding molecular orbital, its stability is low. Okay. And when we are talking about the filling of the electrons in the molecular orbital, it will also follow what? As in atomic orbitals, it used to follow what? The Pauli exclusion principle, Hund's rule, Aufbau principle. Likewise, here also it will be following what in molecular orbitals? Pauli exclusion principle as well as Hund's rule, as well as what? Aufbau principle. Now, coming to linear combination of atomic orbitals, we can say in short LCAO, means Lakao, can say in short. Okay. So now here we can see equation over here. Do you remember psi over here, Schrodinger wave equation? Do you remember that? So this psi has came from there. This is what? The wave function. Okay. Here molecular orbital is equal to what? Psi A plus psi B, because we are saying here combination of orbital is taking place, isn't it? So this orbital of A and orbital of B2, like I will explain you with the example. Okay. So if it is psi A plus psi B, okay, it is what? The bonding. And for the anti-bonding, it is what? Psi A minus psi B. This is constructive in nature, this is destructive in nature. Okay. Now, let us see it with the help of example. Okay. Come on, we will be making what? A hydrogen, we will be taking the example of hydrogen making a molecular orbital. You all know that hydrogen consists of one electron, isn't it? So, one hydrogen over here, we can name it as A, okay, and here one hydrogen is here, right, B, okay. So one electron from here, one electron from here, they will, okay, pair up in this first where? The bonding orbital, okay, and following all the above principle, Pauli exclusion principle and Hund's rule, okay. And so now this is what the bonding orbital, which is psi A plus psi B, okay, and now no electrons are present, so here nothing, okay. So here how it is represented, psi A minus psi B, isn't it? As here low energy, here energy is too high, isn't it? So this is how orbitals can combine together, okay, and this is only what the linear combination of atomic orbital. So we are going to study now about the energy level diagrams of the molecular orbitals. It means how the electrons are arranged in the molecular orbitals according to the energy level. It means according to the increasing energy level. Okay, so first we will be studying about what oxygen and fluorine, these two molecules, they are having what? Atomic number more than atomic number, I am saying, sorry, molecular number, or you can say, because here two atoms are combining, so here electrons will be more than 14, okay. So these all can be studied with the spectroscopic methods also, and from that only it has been taken out, okay. So how we will be arranging it? It is sigma 1 s2 subsecum least energy, then sigma 1 s2, this is in the anti-bonding, okay, then sigma 2 s2, okay, this is in the bonding, and then sigma asterisk, it is said, it means anti-bonding, okay, 2 s2, and then comes sigma 2p z square, okay, and then we are seeing the energy level of 2p x square is equal to 2p z 2p y square is similar, okay, not z beta, it is y, okay, is similar, okay, its energy is similar, okay. And then we are seeing the greater energy level of what the anti-bonding orbital, okay. You can see that pi 2px, and then its energy is equal to the anti-bonding, okay, 2p y, and then at last you see what this energy level of anti-bonding 2pz is the most. So now by this sequence only we will be filling the electrons, okay. So first O2, if I am saying one oxygen has got 8 electrons, so 2 it will be what? 8 into 2, so it becomes what? 16, or 8 plus 8 also you can say, okay. Now increase, first we will be filling up where? In the what? Sigma y, this bonding bonding one orbital, isn't it? So here from one electron comes here, and from here fills up here, then 2 are left, it fills in the anti-bonding, okay. Now coming to, this is for what? 1s, coming to 2s, okay. Here we are seeing one electron from this, another from here in the bonding, and then it fills up, you can see over here in the anti-bonding, okay, orbitals, and here you can see 2 electrons, okay. Now we will be filling where? We are coming now to the p orbital, okay. So in this you will see what we are seeing, the energy level of 2pz is more than px and py, okay. So you have seen, you are seeing over here, one is here and one is here, okay, and inside this you will place these two blocks of px and py, okay. So now how many electrons we have used up till now? It is we are having 16, we have used 2 plus 2 4, 4 plus 4 8. So basically now we are having how many electrons? 8. It means 4 from one and 4 from the other oxygen. Now coming to this next is what? The p orbital, okay. How many electrons are left here now? Only 8. 8 from 4 from one oxygen and 4 from another, okay. Now we will be filling this also with the same principle of what? Pauli exclusion principle and Hund's rule, okay. So first, whose energy is less? This, isn't it? So first it will be filling with 2pz, okay, the bonding orbital, and then we are seeing what? This px and py, okay. So then you will be filling in the same way. First you will be filling one in x and then another in y, and then again you will coming back to this x and then y, okay, because you have to fill accordingly, according to Hund's rule. First it will be singly filled and then pairing takes place, okay. And then we are saying where it will be formed. Now here in the anti-bonding, so only we have used up here. How many electrons we have used? 6. Only 2 are left. You will be filling in the anti-bonding what? Px1 and Py, then Py, okay. And here when you are filling this, naturally all the electrons are now being filled up. So here there will be no pairing, and now all the 16 electrons are filled up in this what? O2 molecule, okay. And this is how we will be filling up the electrons in the O2 molecule, okay. Now here one thing more is there. You have to take out the, if you have to take out the bond order, the formula is half the number of electrons in the bonding orbital minus the number of electrons in the anti-bonding orbital. So if I am talking about oxygen, okay, so let us calculate it, half, and now come on, let's see how many electrons are there in the bonding. It is 2 plus 2, 4, isn't it? 4 plus 6, it is 10. 4 plus 6, it is how much? 10, okay, write 10 directly. Minus, let us see in the anti-bonding, 2 plus 2, 4 plus 2, 6, okay. So now 10 minus 6 is 4, so 4 upon 2, that is 2, okay. So bond order of O2 molecule is what? 2. Now let us see whether it is paramagnetic or not. Here you can see, I had said you, if they have got what? Unpaired electrons, they show the property of paramagnetism, okay. So this O2 molecule is paramagnetic in nature because it has got unpaired electrons in them, okay. Now let us study about the energy level diagram of the molecular orbitals for the molecules having what? Electrons less than or equal to what? 14, okay. So I have taken the molecule of N2. It consists of how many electrons? It will consist of 14. 1, and nitrogen consists of 7. 2, 7 plus 7, 14, okay. Now what will be the criteria of filling up the electrons? It is what? Sigma 1s2, okay, the least one energy, then sigma asterisk, it means anti-bonding 1s2, okay, then bonding 2s2, and then anti-bonding 2s2, okay. Then we are seeing what? This pi 2p x square is equal to pi 2p y square, okay. And then we are seeing of what? Bonding 2p z square, okay. And here you are seeing in this the anti-bonding, okay, 2px is equal to anti-bonding 2py, and then what? The anti-bonding 2pz. So you are seeing basically what? This 2pz anti-bonding orbital has got the maximum energy, okay. So it will be filled at the last only, okay. So accordingly the sequence only we will be filling the electrons. So coming this, what is this? Increasing energy level, okay. So now here first we will be filling what? This 1s2, the bonding and the anti-bonding, okay. 14 electrons are there. We have taken in the first 4. Naturally first bonding will be filled and then anti-bonding, then coming to what? This 2s2, okay. In this first bonding will be filled and then anti-bonding. So basically we have used how many? 2 plus 2, 4, 4 plus 2, 6, 6 plus 2, how many? 8 electrons we have covered up out of 14, okay. Now coming to the rest which has been left, okay. So 8 has been covered, so how many are left? Basically only 6, isn't it? So it will be filled in which? The p orbital, okay. So 6 it is, so it will be what? 3 and 3, isn't it? And then again using Hund's rule, Pauli exclusion principle, we will be filling, okay. All the orbitals are filled in that only Hund's rule, weighing the Hund's rule and the Pauli's exclusion principle, okay. So now here let's start filling. First what will be filled? This you are saying this pi 2px and py, isn't it? First we will be filling it singly and then pairing it up if electrons are there, and yes, in this electrons are there, so it will be paired there. And then you are going to fill what? The bonding what? 2pz, isn't it? So in this 2pz it will be filled and naturally 4 has been occupied, only 2 is left, so it will be filled over here. Okay, so now let us take out the what, the bond order. Okay, I said to you what, half NB minus Na, this formula we used. Okay, so half, and bonding, come on, 2 plus 2 4, okay, 4 plus 6 10, minus anti-bonding 2 plus 2 4. So it is coming how much? 10 minus 4, 6. 6 upon 2, it is 3. Okay. Is it diamagnetic or paramagnetic? You can see the electrons are paired over here. So what it is? It is diamagnetic in nature. Okay. So only hydrogen bonding has been left in this chapter. We will be dealing in it in states of matter along with other bondings. Okay. And now we are ending this chapter. Hope you might have understood it. Good day. Take care.